This particular section in Chapter 6 deals with acid-base chemistry. Here are some examples of chemicals in your kitchen or your house that are acidic, and chemicals in your house or around your house that are basic. Acids are generally chemicals that taste sour. Dehydrate substances. Dehydrate basically means removes water. Neutralize bases. Dissolves metal and turn blue litmus paper red. Litmus paper is an acid-base indicator. They come either in red or blue color. If you have blue litmus paper and you expose it to acid, the blue litmus paper will turn red. Examples of acids are juices, tomato juice, orange juice, apple juice, wine, slightly acidic, banana, coffee, vitamin C. Vitamin C is actually ascorbic acid, and soda has a lot of phosphoric acid and carbonic acid. Base are chemicals that taste bitter. They denature proteins. Denature means that they break down proteins' structure. They neutralize acids and turn metals to hydroxides. They also turn red litmus paper blue. Examples of base chemicals are lime water, milk of magnesia, which you generally take if you have an upset stomach because of acid buildup. Lye or Drano are chemicals that you put down your drain to eat up the food. Ammonia, blood is slightly acidic, and soap is also, blood is slightly basic and soap is also basic.
Concentrated sulfuric acid is going to be used to dehydrate sugar. First, sugar is moistened with water. And then concentrated sulfuric acid is added. As the acid goes in, the sugar quickly darkens because water is removed from the sugar and black carbon is formed. The removal of water from the sugar by concentrated sulfuric acid is an exothermic process. We soon begin to see steam formed. As the steam mixes with the carbon, it forms a black pillar which rises high above the beaker as the mixture heats and expands.
This is an example of how acid dehydrates substances like sugar. It basically removes the water. A definition of an acid was first proposed by Arrhenius, and Arrhenius defined an acid early on as any chemical that increases H plus or H3O plus concentration. H plus is also called a hydrogen ion, or when it combines with water, H2O, to form H3O plus, it's called hydronium. Base are chemicals which increase OH minus or hydroxide ion concentration. Those are the Arrhenius definitions of acids and base. And these are limited to aqueous solutions. Examples of substances that are able to ionize to hydrogen ions and thereby increase the hydrogen ion concentration are like HNO3, which you guys know as nitric acid. When you put that in water, it dissociates, that is, it breaks up into its ion, H plus and NO3 minus. You probably recognize the NO3 minus as nitrate. Bases are substances that accepts or react with H plus and combines with it. Hydroxide ions, OH minus, are basic because when they combine with H plus, as shown in this reaction, you form water. As I said, H3O plus is called the hydronium ion. So when you have an acid and it dissociates to H plus and Cl minus, this actually takes place in the presence of water. And so what actually happens is that as the electron is ripped off a hydrogen atom, that hydrogen atom is going to be H plus, which is very reactive, and it combines with H2O molecules, and that H3O plus chemical is called the hydronium ion. And here what you see is the reaction in which H plus and water combines. In chemistry, we interchange the terminology of protons or hydrogen ions with hydronium ions. And remember, this takes place in aqueous solution. This only takes place in aqueous solution. We have the definition of strong acids and weak acid. The definition of strong acid and weak acid has nothing to do with concentration. If you have a 1 molar acid, that's just very concentration. If you have 10 to the minus 6 molar acid, that's weak, low concentration of acid. But the definition of a strong acid and a weak acid has to do with the chemistry. When a chemical breaks up into its ions 100% of the time, or dissociates 100% of the time, we define that chemical as a strong acid. Examples of strong acid, and make sure you remember this, are sulfuric acid, right here, nitric acid, perchloric acid, and chloric acid. Other strong acids are the halogenated acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. These 1, 2, 3, 4, 5, 6, 7 acid for this class are your strong acid. All other acids you can consider weak. Weak acids are chemicals like acetic acid shown here, that if you put it in water, it doesn't release its hydrogen 100% of the time. In fact, for acetic acid, it only dissociates 1% of the time. 1 in 100 breaks up into its ions.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it is not completely ionized. It is therefore termed a weak electrolyte, or weak acid.
So in that example, you saw that nitric acid and hydrochloric acid are strong acid because when you stick it in water, they separate 100% of the time. Acetic acid, on the other hand, if you have 100 of those acetic acid chemicals, only 1 in 100 will dissociate. What are strong bases? Strong bases are those chemicals that delivers hydroxide 100% of the time. So just like strong acid, if you have a chemical that when dissolved in water gives you 100% hydroxide, then you can consider that a strong base. Strong bases are generally made out of a metal, especially group 1 metal and hydroxide. The alkali metal, sodium hydroxide, potassium hydroxide, lithium hydroxide, or group 2, calcium hydroxide, barium hydroxide, and strontium hydroxide. The other way bases are formed is by extraction of hydrogen from water. When that occurs, as shown in this example, ammonia is a base because it strips the hydrogen of water and you form hydroxide. See how hydroxide is generated? That's considered a base. Sometimes what happens is that an ion like carbonate ion removes the hydrogen from water. You form, in this particular case, the bicarbonate ion and hydroxide. Again, hydroxide is generated. So carbonate ion, CO3 2- is considered a base. Other way of base forming is by the complete dissociation of metal hydroxide, as shown up here. When sodium hydroxide dissolves in water, it separates into the ions, and again hydroxide is formed. In all three examples, because hydroxide is formed, these are considered base.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base. It is also, of course, a strong electrolyte. Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the ammonium and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left. At any given time, most of the ammonia is in a non-ionized form.
So those are examples of how hydroxide is formed by these chemicals. Now there's another definition of base, and this is the more general definition. This definition of acids and base are called the Bronsted-Lowry acid-base definition. And in the Bronsted-Lowry definition, acids are proton or hydrogen plus donors. So any chemical that can deliver H plus to another chemical is considered an acid. Base, on the other hand, are chemicals that accept hydrogen ions or proton acceptors. Example of this is the following. If you put HCl in NH3, what happens is that the HCl dissociates to H plus and Cl. The H plus can combine with the NH3. As you see right here, you get NH4 plus and Cl minus. So in this example, what you have here is that the HCl is the acid because it's the proton donor. NH3 is the base because it's the proton acceptor. Another example is HCl with NaOH. What will happen is that the H plus will react with the OH minus, and so this will give you H2O. H plus is the proton donor, the NaOH is the proton acceptor. Now, you have many types of acids out there. These are example. The first one is hydrofluoric acid. This is nitrous acid, not nitric. Nitric is HNO3. Nitrous is HNO2. Benzoic acid, acetic acid, hypochlorous acid, hydrocyanic acid, and phenol. What makes these acids special is because these are all weak acid. And the way you figure out which of these acids is the strongest is by something called the Ka value. When the Ka value is large, you've got, and notice that all these numbers here are less than 1. weak acids will generally have Ka values of less than 1, okay, but not negative. This is 6.8 times 10 to the minus 4, 4.5 times 10 to the minus 4, 6.5 times 10 to the minus 5. The smaller the Ka value, the weaker the acid. 1.3 times 10 to the minus 10 is a lot smaller number than 6.5 times 10 to the minus 5. Therefore, phenol is a weaker acid than benzoic acid. Hydrofluoric acid is a stronger weak acid than nitrous acid. Here are acids that can deliver more than one hydrogen. Sulfurous acid and sulfuric acid are strong acid in this category. They give up their first hydrogen with these values, and then they give up their second hydrogen, and you notice that the Ka2, the release of the second hydrogen, is much less efficient than giving up the first hydrogen, and some of these chemicals will give up a third hydrogen. So these are called polyprotic acid because they can deliver more than one hydrogen. Now water actually takes on both acids and base property. Water has a way of what we call auto-ionization or self-ionization. So the question I like to ask my class is, why does water have a pH of 7? What is so magical about a pH of 7? Many students will say, well, pH of 7 means neutral. But why is it neutral? Well, the reason why water has a pH of 7, and pH, by the way, is an acid strength indicator. It tells you the degree of how much hydrogen ions are in solution. But the reason why water has a pH of 7 is because 2 in 1 billion water molecules undergoes this self-ionization. If you take water molecules and you have them react with itself, one of the water molecules will give up the hydrogen and the other will accept it. So you form H3O plus and OH minus. And this reaction right here has a Kw, which tells you the efficiency of this reaction. The lower the K value, the Kw in this case, Kw stands for water, the lower that number, the less efficient this reaction goes to the right. The bigger that number, the more efficient, the more likely that reaction will go to the right. Well, guess what? Water has a Kw of 1 times 10 to the minus 14. And what does that translate? It translates to the fact that when these things undergo the self-ionization with this Kw value, then the concentration of hydronium and hydroxide in water, pure water, is 1 times 10 to the minus 7 molar, both for hydronium and hydroxide. It's actually temperature dependent. What happens is that Kw becomes much more efficient at higher temperature. In other words, this reaction becomes better as you increase the temperature and becomes less efficient when you lower the temperature. But remember, these are still very small numbers. 0.29 times 10 to the minus 14 is not that much different to 5.48 times 10 to the minus 14. The take-home message here is that the self-ionization of water is temperature dependent. The higher the temperature, the better that reaction takes place. Now, how do we determine the concentration of hydronium and hydroxide when you just have water standing there? Well, it's actually a little bit of math. We know that the concentration of hydronium and hydroxide is equal to the Kw. So, for every 1 hydronium, you form 1 hydroxide. So if you do the algebra, that means hydronium and hydroxide are equal. And so if hydronium and hydroxide are equal, then you can set this up so that what we have is X times X, which we represent to represent the hydronium and hydroxide concentration, is equal to 1 times 10 to the minus 14. And so if we do that and solve this math right here, we see that the X value, which is hydronium and hydroxide, is 1 times 10 to the minus 7 molar. And if we take this number, 1 times 10 to the minus 7, and we take the negative log of that number, we get the value of 7. And that negative log number is called the pH, as you see right here. So we can summarize what happens with water, because there's always going to be hydronium and hydroxide present in an aqueous solution. The more hydronium you have, the more acidic the solution. The more hydroxide you have, the more basic your solution. So if you have a solution in which the hydronium ion is 1 molar, then if you take 1 and take the negative log of that, just take the negative log of this number right here, you get 0. And it so happens that the pH and the pOH equals 14. If you have the concentration of hydronium of 1 times 10 to the minus 7, that's what this is, and you take the negative log of this number, then the pH is 7. And remember, the pH and the pOH always adds up to 14. So 7 plus 7 equals 14, 0 plus 14 equals 14. And so if you've got a 0.1 molar solution of hydronium, 1 times 10 to the minus 1 molar hydronium, and you take the negative log of that number, then the pH is 1. That makes the pOH 13. If you take a solution that is 1 times 10 to the minus 4 molar hydronium, the pH is 4, the pOH is 10. Over here, if you've got lower concentration of hydronium, 1 times 10 to the minus 10, and you take the negative log of this number, you get a pH of 10. 10 plus what equals 14? 10 plus 4 equals 14, therefore the pOH has to be 4. So you can use this quick scenario, this quick calculation, to get the pH and the pOH of any solution if you have the hydronium ion concentration. In fact, this is the relationship. If you take the negative log of 1 times 10 to the minus 14, you get 14. And the pH plus the pOH equals 14. And that comes from the math, because hydronium times hydroxide is 1 times 10 to the minus 14. So the question here is, what is the pH of a potassium hydroxide solution with a molar concentration of 3 times 10 to the minus 4? Potassium hydroxide is a base. How do you know? Because it's got hydroxide in it. So if you take the negative log of 3 times 10 to the minus 4, what you get is that right there is going to be your hydroxide ion concentration, 3 times 10 to the minus 4. The calculations will show that if you take negative log 3 times 10 to the minus 4, you get 3.52. That 3.52 is actually the pOH. And so what plus 3.52 equals 14, and what happens is that number is 10.477. So the pH of this solution is actually 10.47. Here's another example. What is the pH of a solution that has a hydroxide ion of 3 times 10 to the minus 13? Well, you know that pH plus pOH equals 14. So if I take 3 times 10 to the minus 13 and take the negative log of that, what happens is that number comes out to 12.52 as shown right here. what plus 12.52 equals 14? That number has to be 1.48. Another way of doing this calculation is plugging it into this equation right here. We know what the hydroxide concentration is. It's 3 times 10 to the minus 13. We know what the Kw is. It's 1 times 10 to the minus 14. So if we solve this for hydronium, we get 3.33 times 10 to the minus 2. And now if we take the negative log of that number, we get 1.48. Whether you use this equation right here or this equation right here, you get the same answer. And this right here is a flow scheme of the relationship between hydronium, hydroxide, pH, and pOH. Use this as a handy tool to calculate 3 of the 4. Given any one, you can calculate the other 3. The relationship between hydronium and hydroxide comes from this relationship right here. Hydronium times hydroxide equals Kw. So if you have the hydronium, you take Kw divided by hydronium, you get hydroxide. If you have hydroxide, Kw divided by hydroxide, you get the hydronium. Here, this is much easier. pH plus pOH equals 14. So if you're given the pH, subtract 14, subtract the pH from 14 and you get the pOH. If you're given the pOH, subtract the pOH from 14 and you're given the pH. Now what's the relationship between pH and hydronium? It's a negative log value. Given the hydronium and you take the negative log of that number, you get the pH. What's the relationship between pH and hydronium? It's the inverse negative log, or power of 10. So you take the negative pH and you raise it to the power of 10 to get the other. Likewise for hydroxide and pOH. Here's an example. Go ahead and read this problem and study the solution. And what you will see is that it's basically what we just talked about. Now let's shift gears and let's get away from the calculation. Rainwater is generally not a pH of 7. And the reason why when rain falls from the sky it's not a pH of 7 is because it's really not neutral. What happens is that you have carbon dioxide in the atmosphere. Carbon dioxide will react with the water as it falls from the sky, from the clouds, and form carbonic acid. So rainwater is actually slightly acidic because of the carbonic acid presence. And so the overall reaction is carbon dioxide plus water produces bicarbonate, and that is the acid in rainwater. Now let's discuss how acid rain originate. Suppose you live in a mining town where they burn a lot of coal. Well, coal has a lot of sulfur in it, and when you burn coal in the presence of oxygen, you form sulfur dioxide, and sulfur dioxide will react with oxygen further to form sulfur trioxide, and when it rains, that sulfur trioxide will react with water to form sulfuric acid. And so that's how sulfuric acid can arise from areas that burn coal as a fuel. In places that don't burn coal as a fuel but instead have a lot of cars, and the cars pollute the atmosphere, well, nitrogen and oxygen combines in the internal combustion engine to nitrogen dioxide. Nitrogen dioxide will react with water to form nitric acid and nitrous acid. Again, these are chemicals that are acidic. Here's an example of George Washington statue made out of marble back in 1944. Over a 50-year period, George Washington looks like he has leprosy. But really what happened was that he is exposed to acid rain. In fact, whole forests can die out because of acid rain. In general, if you look in your kitchen, you'll find a lot of chemicals that are either acidic or basic. Chemicals that are acidic have pH less than 7. Chemicals that are basic have pH greater than 7. And here are some examples of common chemicals in your house that are acidic. Battery acid, hydrochloric acid comes from your stomach, or muriatic acid, which is a swimming pool cleaner. Lemon juice, vinegar has a pH of 2. Grapefruit, orange juice have a pH of 3. Tomato juice, acid rain, pH of 4. Soft drinks, black coffee, pH of 5 generally. Urine and saliva, about a pH of 7. Pure water, uncontaminated, not rainwater, has a pH of 7. Seawater, slightly basic, pH of 8. Baking soda is actually basic, pH of 9. The Great Salt Lake, milk of magnesia, is very basic, pH of 10. Ammonia has a pH of 11. Soapy water, pH of 12, some cases. Bleach and oven cleaner, pH of 13. And liquid Drano cleaner, pH of 14. Buffers? Well, buffers are solutions which resist pH change. And the reason why they do that is because the only reason why a chemical would undergo drastic pH change is because there are hydrogen ions present in that solution. So what a buffer does is it removes the hydrogen ion in that solution. Your blood is an example of a buffer solution. In fact, it's buffered at 7.35 to 7.45. If it deviates from those values, those pH values, then you can get very sick. The way it works is that there are proteins in your body that chews up acid. There's also phosphate ions in a ratio of 1.6 to 1 that chews up H+. But more importantly, you have carbonate ions. Carbonate ions and carbonic acid that tends to chew up H+ and OH-. The chemistry is this. If you've got excess acid in your body, then the bicarbonate in this chemical, carbonic acid, will remove the hydrogen from that acid and form carbonic acid and water. Now you might ask yourself, well, aren't I just substituting one acid over another? Yes, you are, but this right here is a strong acid, H3O+. H2CO3 is a weak acid, and your body can eliminate H2CO3 by you just breathing it out. It breaks down to water and carbon dioxide. On the other hand, if you've got too much base in your body, then the conjugate chemicals of bicarbonate, which is H2CO3, reacts with the hydroxide to form bicarbonate. And so, again, it removes the OH-, it forms water. And so, the pH does not change. Remember that the pH of a solution will change only when you have a change in hydronium ion or hydroxide ion. In these reactions, both the hydronium and the hydroxide is removed. Therefore, the pH doesn't change. So, what happens if your blood pH drops below 7.35? Well, then you have acidic blood, or also called a medical condition called acidosis. What are the symptoms of acidosis? Well, it's a depression of the acute nervous system. You have fainting spells or coma, and eventually you die. What are the causes? Respiratory acidosis. You have difficulty breathing, and so you can't break down the carbonic acid to H2O and H2O and carbon dioxide. The carbonic acid will instead release hydrogen ions. And so If you have difficulty breathing, you'll get acidosis. In fact, you can, next time you have your blood test, you can give yourself acidosis by just holding your breath. The mechanism, of course, is that the carbon dioxide doesn't leave your lungs, which results in the buildup of H2CO3. Metabolic acidosis can occur because you starve yourself, in which case you have a buildup of lactic acid. If you starve yourself, then you start breaking down fatty acids, and heavy exercise results in lactic acid. If your blood pH goes above 7.45, then you have a health condition called alkalosis. The symptoms of alkalosis is overstimulation of the central nervous system, muscle cramps, convulsion, and eventually death. What are the causes? Well, respiratory alkalosis. You have heavy breathing. So what happens is because of fear, hysteria, fever, infection, you release the excess carbonic acid from your body, and that lack of carbonic acid means that your blood pH is less acidic. So how do you remedy this? Well, you breathe in a bag and you breathe back in some carbon dioxide, so it reacts with the water in your body to form carbonic acid. The metabolic alkalosis, basically you can induce it by having vomiting episodes, in which case you eliminate natural acids from your body. So the way buffer system works is because it removes the hydronium and hydroxide, therefore the pH doesn't change. If you have excess acid, the bicarbonate ion will react with it and you form carbonic acid and water. The excess carbonic acid you breathe out. As shown in this mechanism. If you've got excess hydroxide, then the hydroxide reacts with the carbonic acid and breaks it down to bicarbonate and water. We're now going to shift gears to titration. Titration is a technique by which you can determine the acid content of a solution by treating it with a known concentration of acids or base. What happens is you take a sample that you're going to analyze, you measure the volume, you put it in an Erlenmeyer flask, then you add, if this chemical is an acid, you add a predetermined amount of base, the opposite chemical, and you figure out what volume of base is necessary to make this solution neutral. If you know the volume and you know the concentration of the chemical you're adding, you can calculate the concentration of that original chemical you were analyzing. What you generally do is you put an acid-base indicator in the solution, and once that chemical turns from acid to base, the color changes. Here are examples of acid-base indicator. There are many types. Here is a titration in which we have a chemical being titrated, and once you hit neutralization, that chemical turns to a color. When it goes from acid to base, that changes the color of the solution. An example of a acid-base indicator is phenolphthalein. This is a titration curve. What happens is that the chemical being analyzed, the acid being analyzed, is acidic, but once you add enough base in here so that the solution goes from acidic, notice the pH is less than 7, to basic, there is a color change. And this is a graph of pH versus the chemical that's being added into the solution called the analyte. Here's an example in which we have 20 mils of acid, that's this right here, is being titrated with 0.0982 molar sodium hydroxide, that's this chemical right here, and it takes 18.34 mils of sodium hydroxide. Question is, what is the concentration of the hydrochloric acid? We can easily see that if we know that the sodium hydroxide is 0.0982 moles per liter, that's what molarity is, and we use 18.34 milliliters of that, then we can calculate the concentration, because the moles of the hydroxide is equal to the moles of the acid, and if we divide by the volume of that acid that we titrated, we have the concentration of that acid. And this is a summary of acid-base chemistry and the things that we talked about.